Mr. Gustin back in the physics classroom. Today, what I want to talk about are the specific or the three kinematic equations we have and exactly as they appear on your equation sheet, what those variables mean, how I can use them. Because sometimes in class or in textbooks or online, they're written a little differently than they appear on the equation sheet. So I want to talk about what these variables mean specifically. Okay? So first things first, if you notice on your equation sheet, actually, this middle column tells you pretty much what all the variables mean, but they don't have all the subscripts. They don't have this x and x0 and stuff. So let's go ahead first and figure out what these variables mean, and then figure out why the heck they have these subscripts in these equations. Okay, so the very first variable we come across is t. T is time. Time is the amount of time this equation, or this scenario we're using the equation for, the amount of time this equation is encompassing. Okay, so if I'm talking about I start from rest and I accelerate for 5 seconds at a constant rate, that 5 seconds is the time. If I jump up and fall back down like I would in the hang time lab, and all I'm concerned about is the amount of time I jumped up for, well then this time variable would only be the time I jumped up for. It wouldn't be the total time. Okay, so the time kind of bookends or tells us what the equation is going to be, kind of the spread of the equation, how wide that equation is, what that equation is trying to explain. That's our time variable. The next one is acceleration. That's A. And acceleration is by definition the change in speed over time. It's how quickly the rate of speed is changing, right? The rate at which speed is changing. That's what it means, okay? It is how quickly something is either speeding up or slowing down. In this class, accelerations will always be constant. The other variable we see here is x. X is technically position. It is location in space. Now, x can actually sometimes be referred to as y, based on which direction we're moving in. So we have the x direction, which is typically horizontal. We have the y direction, which is typically vertical. All of our equations here are written in terms of x, but sometimes you'll see y show up. Y in place of x just means we're moving vertically. Typically, when we're moving vertically, this acceleration is actually g, or baby g, 9.8, the acceleration due to gravity. So position might appear as either one of those, but x is position. The final variable we see here is v. And v on this equation sheet is technically speed, but we like to call it velocity because we like to use direction when we here in our physics class. So it's velocity or speed, but I want to call it velocity now, okay? So these are the equations that we have. Let's talk about what they mean in terms of mathematics, variables, and even descriptive. Like, what does it mean to describe this expression? Let's start with the first one. The first one is our linear equation. It comes from the graph of velocity and time, because velocity and time when an object accelerates is linear. So what does it mean? It means this. If I look at this very first variable here, this very first variable is velocity sub x sub 0. What this means is that this is the initial. The 0 means initial. It really means at time 0. When time is 0, what is the velocity in the x direction? So this little 0 indicates velocity. Time is 0. The v indicates velocity, and the x indicates the direction it's moving in. So I put it all together. This variable is the initial velocity in the x direction. That's all that means. That's what that variable means. And the reason it's the x direction is because, as we see shortly, this a is the acceleration, and probably should be written as ax. This acceleration is the acceleration in the x direction. And this final velocity is, again, in the x direction. This is the velocity at time, at t, in the x direction. And of course, t is time. So what I want us to understand here is that this equation works. The final velocity, or velocity after a certain amount of time, is equal to the initial velocity in that direction plus the acceleration in that direction times the total time it took for the motion to happen. This is true. Now, this equation can very simply be changed to the y direction, where all of these times, or these variables and accelerations, are in the y direction. However, this equation does not work and will not work if we are using initial velocities in the y direction, or we're using accelerations in the y direction. We can't use opposite directions in the same equation to produce a meaningful answer. It doesn't work because that's not what this graph says, and that's not what this equation is meant to explain. What it explains is the motion, the velocity of an object moving in a direction over a period of time. We pick which direction we're talking about, whether it's x or y, and we move forward with that equation, okay? So in our free fall labs, largely we've been talking about this stuff moving vertically, but earlier on in the year, we were talking about this stuff moving horizontally, okay? This is our first equation. The next equation looks pretty similar. I see some of the same variables. Well, the same variables mean the same thing. So I've got my time. Time is like the bound of my problem. How long is this motion happening for? I see acceleration. Well, this is acceleration in the x direction. Okay? This is my initial velocity in the x directions. What speed did I start at in this direction? And then I see my two position variables. And position variables are interesting. What it basically says is the location that I start at is when time is 0. So it doesn't matter if it's 0 or not, but it's where did you start when time was equal to 0 seconds. Maybe you started at 100 meters and moving forward. Maybe you started at 30 meters and moving backward. Maybe you started at the top of the building and you were 9 meters in the air, and you're going to call that 9 meters, and on the way down you're approaching 0. Your initial position would be 9 meters at the top of the building, and your final position, or your position after a certain amount of time, would be equal to 0 meters, which would be the ground. This, again, is the bound of our problem. Whatever the motion is over this time interval tells us which variables we should be plugging in, or the numbers for these variables, okay? So the only new variable here that we're noticing is this initial position in the x direction and the position at t in x direction. Again, we can go ahead and use our y variables as well. This could be y is equal to y0 plus vy0t plus 1/2 a yt squared. Again, based on the direction we're moving in. Lastly, the only new variable we see here is not even a new variable, we see a new way of talking about it. We see this position final minus position initial. Well, this is what we call a change, or a delta x, change in position. We could also see it here if we subtract our x initial over, we can call it delta x, and sometimes I'll even write it that way. I'll write it delta y, or delta x equals v naught t plus 1/2 at squared. Over here, this expression is a relationship between velocity in one direction and the change in position in that same direction. So here, again, I have my initial velocity in a direction squared plus 2 times the acceleration in that direction multiplied by the change in position in that direction is equal to the final speed in that direction. The biggest takeaway from this is that our equations have to be explaining or describing motion in either the x or y direction. We cannot overlap directions, okay? So this is just a real brief kind of rundown recap on what these equations mean. Not so much where they come from, but what they mean in terms of mathematics, what the variables mean. And I hope that if you're struggling at all with these equations, this helps you a little bit at least. All right? See ya!